Hi, welcome to the video on equilibrium in 3D. And we are going to discuss, or I am going to ask you to think about how things move in 3D. What are the degrees of freedom? In 2D, right, things can go, let me just, I think green is better. Green is better actually on a blue. So in 2D, we can have movement in the vertical axis, movement in the horizontal axis, and rotation, right, like this. Now in 3D, right, we can have, if this is x, y, and z, we can have translation in x, we can have translation in y, translation in z, rotation, right? Rotation about the x-axis, rotation about the y-axis, and rotation about the z-axis. So in 2D, we have 3 ways of movement. In 3D, we have 6, right? For 2D, we had sum of forces in x equal to 0, sum of forces in y equal to 0, and sum of moments equal to 0. For 3D, we have sum of forces in x equal to 0, sum of forces in y equal to 0, sum of forces in z equal to 0, and 3 moment equations. Sum of moments about the x-axis equal to 0, sum of moments about the y-axis equal to 0, and sum of moments about the z-axis equal to 0. So 6 equilibrium equations, right? So about how to handle three-dimensional case, right? The same things apply, right? The supports will provide you with a reaction force, right? Every time we prevent a translation, we have a reaction force. Every time we prevent rotation, we have a moment reaction, right? And for 3D, we have several tools to handle them, such as CDN format. We can express vectors as magnitude times the unit vector that runs along the direction of the force, or express it in terms of magnitude and cosine direction, right? So the tools are there, right? And then different types of supports in 3D will provide you with different reactions, right? Different reactions. So let's just examine maybe just a couple of these two, right? You can take a look at this table later. The ball and socket, right? Let's take a look at this one, for example. You would agree with me that that figure seems quite right. One may think that all the rotations are allowed, and you'll be right. Only the translations are prevented, right? So only 3 unknowns, right? 3 translational reactions, right? In this type of support. What about this one, right? The single journal bearing, right over here. The single journal bearing. Take a look at the way this support prevents movement, right? Movement. Well, it doesn't let that rod to go up, so that's one movement prevented. It doesn't let it go this way as well, right? It doesn't let it rotate that way. It doesn't let it rotate that way. So that is 4 reactions. But, right, this rod can slide left and right, back and forth, right, back and forth. So there is no reaction there. And this rod can actually rotate, right? So these 2 guys are permitted, right? But these translations, 1, 2, right, and these rotations, 3 and 4, are our reactions. So that's why it says 4 unknown reactions. So I encourage you to take a look at this table, right? And then some of these cases are very self-explanatory, right? You have to take a look at what types of movements are prevented, and then when you prevent a movement, you create a reaction force. Now, once you have taken a look at your reactions, right, the next step is to apply your equilibrium equations. How many did we say? 6, right? You will have 6 equilibrium equations, which means that you will be able to solve up to 6 unknowns, right? 6 unknowns. So in the next couple of slides, right, it's just presenting some examples on a given situation, and then in the next example is how to develop the free body diagrams, right? The only thing you have to be careful in here is to always make sure to imagine in 3D, right? Imagine in 3D, and now imagine that there are in fact 6 types of movement, right? 3 translations and 3 rotations, right? So inquire with your instructors if this is something that you should study for your assignments or your labs, right? They will be able to tell you. So thank you very much, and see you on the other side, right? The next video, in which we will take all this knowledge we have acquired now about the reactions, and the next step is to actually go inside the rigid body. And we said, you know what, don't worry about internal forces, they cancel each other out, right? So don't worry about the moments they produce because they cancel each other out. But let's see, yeah, they cancel each other out, but how big they are or how small they are. What sort of internal forces? We haven't said that the internal forces are 0, right? What we said is that the effects caused by the internal forces cancel, right, inside the body. But when we take external equilibrium, but we don't really know, right, what sort of internal forces develop in the members. And these internal forces are really important in order to design these elements, right? If you have a lot of tension inside your rigid body, you have to provide a good material that is able to resist tension, right, of a certain shape, of a certain dimensions. So the next step in our journey will be to take a look at rigid bodies. We will calculate reactions, but then we will go one step beyond, and we will calculate internal forces, right? Internal forces in the members, and we will start investigating from the simple cases, right? Structures called trusses, onto a bit more complex structures called beams, right? So these will come into the next series of videos. Thank you very much. See you on the other side.